now that we are experts at drawing Lewis structures, we can look at the molecular shapes and electronic shapes of these molecules, right? The so-called VSEPR theory, valence shell electron pair repulsion rule. So if you do have some molecular model set from organic or from Gen Chem, I highly recommend that you pause and go get it. If not, maybe order one real quick from Amazon. There are some $20 ones. It would be ideal for you to have trigonal bipyramidal centers as well as octahedral centers. It's really going to come in handy. It's definitely going to come in handy for the following lectures when I talk about point group theory, and visualizing in 3 dimensions isn't easy, and so I highly recommend that you purchase a set. I should have mentioned that earlier. Or if you have it, bring it out. If not, get some gummy bears and toothpicks. It works too. All right, so VSEPR theory, again, big word, valence shell electron pair repulsion rule. All that means is that you either have your electrons tied up in a bond here or as a lone pair in a shell, right? So either way, these are all shells, right? Whether they're bonded to an atom or they're occupying an orbital, a hybridized orbital in this case, they are going to repel each other, right? So the repulsion. And they're going to go as far away as possible from each other. That's all that means. There's an excellent book. It's very old, but it's excellent, and it's got some great examples in it. I don't know if your library has it, but you know, it's an actual book with pages and stuff. You have to flip through it, but they're resources, so you don't need the book. It's just there because I love it and I'm old. All right, so let's take a look, right? There is a system that we can use if you're really struggling with these molecular shapes and visualizing and figuring out, oh, trigonal bipyramid and so whatnot. You can take any molecule and put it into this ABE system, where B are the bonded atoms and E are lone pair electrons. And then, for example, if we draw the Lewis structure for H2O, and we all know this has a bend geometry, but when you're first exposed to it, you may think this is linear, and you know, there are 2 lone pairs pointing away from each other, and so you may think that. It's kind of hard to visualize that and to realize we have 4 groups of electrons attached. So we have 4 shells, all right? So we have 2 lone pairs and 2 bonded pairs. And so we can stick this into this ABXE system where A is the central atom, so we're always going to have 1. So this would be a central atom oxygen. Bonded atoms, we have 2. There are 2 hydrogens, so this would be A, B2. And then lone pairs, or electron pairs, are 2, so it would be A, B2, E2. And then you can simply memorize that everything that's A, B2, E2 is always going to be bent. And also important here is that X plus Y gives you the occupancy, and that gives you the electronic geometry, right? So here we have 4 different regions. They're going to push us far away from each other to make this tetrahedral shape, right? So electronically, anything that has occupancy 4, as is the case here, that's X and Y together, has a ground or an electronic shape of a tetrahedron. And then of course electrons don't have any matter or negligible matter, so they're just taking up space and they're pressing on the existing atoms. So they're pressing down from above and below, and so we get a bent shape. Okay, so we're going to use this system, and as I go through these different shapes, I'm going to start from a very simple one here. I will also practice drawing Lewis structures. So if you have occupancy 2, there's only one way to do it. You have 2 atoms or 2 groups attached to a central atom. In this case, we have carbon as a central atom. So this has 16 valence electrons, so we end up with an electron deficiency on carbon when we draw single bonds, so we must make 2 double bonds. And so it doesn't matter whether these are double bonds, triple bonds, or single bonds. They all point in one direction. They all occupy one region. So this is AB2, and linear. They go as far away from each other as possible. So we have a 180-degree angle here between the 2. Okay, moving on to occupancy 3. Now we have a couple of different geometries. First of all, if you have through 3 regions, AB3, our electronic geometry is going to be a trigonal planar shape. Like it's basically just a triangle. You have 3 groups pushing away from each other as far as possible. You can see this if you look at it from the top down. It looks like a triangle. If you look at it from the side, you can see how flat it is, no matter which direction you are looking at it. So we'll see how this works. So the example here is, of course, a carbon with 2 methyl groups. So this is a ketone, right? This would be the proper structure. The bond angles here are 120 degrees. Every region, all 3 regions are occupied by an atom, so the molecular shape would be trigonal planar, which in this case is equal to the electronic shape. But when we replace one of these regions with a lone pair, we have still the same electronic shape, right? So now we have a sulfur in the center. We have 2 double bonds, right? We're going to reduce formal charges here. And but even if you choose not to do 2 double bonds, if you have a single bond and still a formal negative charge on oxygen, you still have the same shape, right? We have 3 regions, but one of them is occupied by a lone pair, so this makes a bent shape. And so if you wanted to build your trigonal bipyramid, that's a great starting point. And then if you simply remove everything, of course I'm removing the electrons too, but I'm doing that so you can see the molecular shape here, then this becomes simply a bent molecule. All right, occupancy 4, we now have the tetrahedron. Let me go find one. Here you go. This is the tetrahedron. It has different groups here, but every one of these angles is 109.5. So they push away very symmetrically and make a 109.5 degree angle. So anything that has 4 groups attached, and we've seen examples already, phosphate, sulfate, perchlorate. So I'll just use that as an example. I'm going to do phosphate. Again, I'm going to use the trick. I'm not going to count valence electrons, and I'm just going to recognize that we have 3 negative charges. The more electronegative element is oxygen. So 3 of these 4 oxygens are most likely singly bound, because that would put a -1 charge on each of these oxygens here. And so that would correspond to the overall charge of the polyatomic ion phosphate. And then we have a 4th oxygen, and that goes on phosphorus, and it's going to be double bond. And then our final check needs to be the formal charge on phosphorus. And so we have, I already know it's occupancy 4, it's a tetrahedron, so there isn't a lone pair there, but you do want to check. There's 1, 2, 3, 4, 5, right? These are all sharing, all 5 bonds are sharing. That's half of it is 5, and the valence of phosphorus is 5, so it has a formal charge of 0, which is what we want. So this is the tetrahedral, and so all of those sulfate, perchlorate have that. Again, it is a 109.5 degree bond angle between each of these, whether this is from here to here, right? Because it looks like it's flat and it's 90 degrees, but it really isn't. It pushes away in 3 dimensions like this and makes this tetrahedral shape. Now if we remove one of those bonds and replace it with an electron, so of course you're just removing the atom, right? But I'm going to remove the entire thing so you can see what happens to the shape, right? So we still have these bond angles here, but we're decreasing the bond angle too, because we had a tied up lone pair, and we're just removing the nucleus, and so those electrons are going to spread out. Electrons take up more space than bonded electrons, right? So if you have 2 atoms and 2 electrons bound between them, they stretch between the 2 nuclei. But if you have a lone pair, it can spread out, and it is going to take up more space than atoms. So it will decrease that angle from 109.5 to something smaller, like 107, or it depends really on the molecule. But if I draw an example here, so I'm going to use ammonia, NH3. So we still have an occupancy of 4. We have an electronic shape of tetrahedral. one of these regions is occupied by a lone pair, and so we get a decrease. So basically, we just like the angle, the hydrogen angle is going to be smaller than 109.5. That's the safest way to communicate that. Okay, so that would be a pyramidal shape. All of those have pyramidal shapes. So let's take a closer look at the idea that I just threw at you, right? So here we have ammonium. Okay, so that would be a tetrahedral. The bond angles are 109.5 degrees here. So if we are looking at a nitrogen-hydrogen bond, that electron pair here, which is the sigma bond, is stretched between the two nuclei. Now if I remove this nuclei and I leave the lone pair, there's no electrostatic force pulling that electron pair towards another nuclei, right? So it's simply going to flop and press down on all these bonds. So this lone pair takes up a lot of space and it presses down. And so in the case of ammonia, so this is ammonium, NH4, and this is ammonia, so it's actually going to have 107 degrees rather than 109.5. So that would be this bond angle here. So that's important to note as well. So keep that in mind. Lone pairs take up more space than bonded pairs. And so let's take a look at this phenomenon here, right? So this is group 15. They're all bound to hydrogen. There are, and we're simply going down the group. We're going from nitrogen to phosphorus to arsenic to antimony. We already said that a perfect tetrahedron would have 109.5 degree bond angle, and that when we remove that atom we get a decrease. So all of those have smaller ones, but we do see a trend here. As we go down a group, we see another decrease in that angle. So what that means is this lone pair here is able to push down more than the one from nitrogen. And that is not due to size, that is due to polarization, right? So we are looking at electronegativity. So the electronegativity of hydrogen, of course, is 2.1. And the electronegativity of nitrogen is 3.0. And then phosphorus, we get that huge drop in electronegativity. So that's 2.1, and then 2.0, and then 1.9, right? So we see polarization towards the hydrogen when we replace nitrogen with phosphorus, right? So here we have polarization towards nitrogen. Therefore, the lone pair cannot press down on this electron density that is pulled towards the nitrogen. However, here we have 2.1 and 2.1, so it's pretty even sharing. So the polarization is towards the hydrogens, which allows this lone pair to press down and decrease this bond angle. So that's a pretty important concept. And then as we replace phosphorus with arsenic and antimony, we do see a little bit of an increase, but we also don't see a huge decrease in electronegativity. So that is pretty much still even sharing of electrons. So that's a pretty important concept here. So let's take a look at another bond angle. So here we go, same idea, same concept. It is polarization. So again, we have 3.0 here in the center, but this time we are using different halides here. We're using chlorine and fluorine. So fluorine is much more electronegative. It has an electronegativity of 4.0. It's going to pull that electron density away from the center towards the fluorines, which allows that lone pair to press down and decrease the bond angle. Same argument here, except now phosphorus is replaced with nitrogen, so phosphorus already has a more, it's already enough polarized towards the chlorine between phosphorus and chlorine, so you don't see much of an increase in here. So a lot of times students will think this has to do with the size of the atom that you're replacing, but it really isn't that. Okay. Moving on to, oh yeah, we're not done removing lone pairs yet, right? We had a tetrahedral electronic geometry. And well, I already have a water here. What happened to my other one? Here it is. So this was the AB3E. Now I remove another one, so AB2E2. We already looked at that. That is bent. Electronic shape still tetrahedral. So that's the end of that. And throw it away. So here are 3 examples for bent shape. We're just going down group 16, oxygen, sulfur, selenium. Again, we see that polarization effect. We have polarization away from the center, which allows the 2 lone pairs here now, right? So first of all, instead of 109.5, we decrease this angle. We have 2 lone pairs pressing down, so it goes to 104. And then if we replace sulfur, oxygen with sulfur, we see polarization towards hydrogen. Same concept, same idea, very important to note. All right, occupancy 5, it's the most complex. It's a trigonal bipyramid. So now we have actually 2 different bond angles. All right, so here I have a trigonal bipyramid. So we have a triangle in the center, right? So this would be like trigonal planar, but we're capping the top and the bottom. So here we're looking at the 120-degree angles between the 3 in the center. So let's put some vocabulary on there, right? So if I'm looking at a trigonal bipyramid and I am facing it up and down, right? You know, there's no up and down, but anyway, the ones that are 120 degrees, we call those the equatorial positions, and then we have axial positions on top and the bottom, right? So if we cap a trigonal planar shape on top and bottom, we get this trigonal bipyramid. So we have 90-degree angles between axial and equatorial positions. We have 120-degree angles between equatorial and equatorial positions, but we also have that 180-degree angle between the axial positions. So that makes life a little bit more complicated, but this is called a trigonal bipyramid. I have a very simple example here, PF5, and I don't care how you draw it. You know, I know what the structure is, the shape, so I can kind of draw it 3-dimensional. If I wanted to be even better to emphasize this shape, I would make that a wedged bond coming towards us, and then I would do the dashed bond here. But as I said, I'm not all that interested. For sure, what you need to have when I test you on this, you have got to include all of the electrons. Okay, so you're still an undergrad, you don't have a degree. So when you get your degree, then you can leave those electrons out. At least that's what I was told in the 80s, and some things never change. Okay, include all of your valence electrons, even in a simple structure like that. So that's occupancy 5. We'll talk about hybridization some other century, okay? If you now go to the next example, AB4E, we are going to be replacing either an axial or an equatorial position. So that needs a little bit of thought, right? So what we want to do is, I told you that lone pairs take up more space than bonded pairs. So we want to remove an atom and replace it with a lone pair that allows the lone pair to occupy more space. So our choices are equatorial or axial. And when I throw that question at my students most of the time, and I would do the same intuitively, oh, it's going to go from the top, that's like a half a sphere, and but it's actually not true. I mean, yes, it is a half a sphere. That's a lot of space you're freeing up. But if you are replacing one of the equatorial positions, you do get that half a sphere, but you get a little bit more because there's also that, you remember we have the 120-degree bond angles here, so you're freeing up even more. So it's the equatorial positions that are removed as we replace bonded pairs with lone pairs, right? So we get this so-called seesaw, right? So SF4 is the example. And so I choose simple examples. There's a lone pair here. make sure that you include all of your electrons here. So there should be 6 electrons on each fluorine, so that they all of them get their octet. And that is important for you to include. I will take off points if you don't do that. Okay, so that's AB4E. Now we remove the next one. Again, we are going to remove an equatorial position. Now we get this T, okay? So the next one is T-shaped, and the example I have is ClF4. So it's chlorine, and then 3, and then we have 2 lone pairs here, and fluorine, fluorine, fluorine with 6. You know, those lone pairs are kind of like when they tell you on the first 6 exams for Gen Chem 1, put your units, okay? Show how your units are canceling, right? Include your units, don't just write numbers. Same thing here. Include all of your electrons. Very, very important. So let me ask you this. Do you think that's a true T-shape? Do you think these are really truly 90 degrees? Or do you think that these lone pairs quite possibly push down on that, where that angle is actually less than 90? Okay. We can actually take this one step further and remove one more bonded atom here. And again, this will go from the equatorial position, and then you end up with a linear molecule. There aren't that many examples, but I3- is a good one. So you've got 3 lone pairs on every one of these iodines. And so those 3 in the equatorial position create that linear shape. The negative charge in this case is on the central atom. We don't really have a difference in electronegativity, so electronically there is no preference for that negative charge, and there's plenty of room in the center for that to be. So it's unusual, but there it is anyway. So the next shape is the octahedral. We have AB6 system, and so here we have all bonds are 90 degrees. This is highly symmetrical. There are 6 attached, and so the example here is PF6. Again, I have a very simple example. 1, 2, 3, 4, 5, 6. All angles are 90 degrees, and fluorine, fluorine, and fluorine. So I'm going to leave out, I've got a Ph.D. I'm going to leave out those lone pairs of electrons and call it a day. So then obviously if I go to AB5E, we still have an octahedron, and the one, it doesn't matter which one I remove, they're all the same. So that makes the square pyramid. You've got a square on the bottom, and then a square base. Instead of a trigonal pyramid, we have a square base. Okay, pretty easy to visualize. And now for examples, for Lewis structures, we're actually using xenon. So there's a little bit of a struggle with examples to use. Later when we do transition metals, we'll have no problem finding examples of square pyramids, square planar, and octahedral. We'll have no trouble finding examples. But if we want to use nonmetals and covalent bonds, I realize this is pretty sloppy, but you get the idea. We have, again, we have a lone pair, we have a square base, and so if you draw a line from each of the corners, you get this square pyramidal shape. If we remove the next region, so now we're going to go to an AB4E2 system, we remove the bond on the opposite side, right? So that's as far as you can go with freeing up space. So you now have a square, right? So this is called square planar. It's planar and it's a square, so pretty simple. Still have xenon here as an example. We have a lone pair on top. See, these 2 lone pairs go as far away as possible from each other, and then the other fluorine atoms here they make out the square. So this is called square planar. We can do one more, I think. Let's see what I have. No, I don't have an example for one more. You can obviously keep playing that game, removing where you would have a T, but apparently there is not an example. So this is what I'm showing you now is actually new, I guess. I don't think you went past 6, but we can, of course, have shapes that are past, and we have some examples of where we have 7, 8, 9 atoms attached to the central atom. We'll have to have a rather large central atom. Here uranium is pretty large compared to fluorine, so we have 7 fluorines. I guess that would be a negative charge, a negative 2 charge, so that's a typo here. UF7, and then the cyano compound with vanadium here. So anyway, so that would be one of the options for AB7 is the pentagonal bipyramid. That one is pretty easy to visualize. You have now have 5 atoms in the equatorial positions, and then one on top and the bottom. So that's your 7. There's also a capped trigonal prism that's also has AB7, and then there's a hexagonal pyramid. So you have 6 in the base and then just 1 up top. So there's all kinds of funky shapes. No example here. Take note. It's just a shape that's possible mathematically. The easiest one here, actual example, UF7. It's hard to draw as a Lewis structure and make it 3-dimensional, but you can kind of see. Here's your pentagon in the middle, and then you cap it on the bottom and the top, and you get this kind of looks like a diamond here. So it's a pentagonal bipyramid. A capped trigonal prism, okay? You can kind of see the prism here, right? So 2 triangles connected. That's what I was trying to do here. Okay. It's harder to see here, but here you can kind of see that shape, and then you cap it on the top, and so that's called a capped trigonal prism. This is the example of the hexagonal pyramid. Note the lack of compounds that represent that, so we don't really have examples for that, but it's not that difficult to visualize. We can actually go to 8. We do have some. It's pretty rare, but we do have some examples here involving molybdenum and tantalum, and so if you imagine a cube, you know that's 8. It makes sense, but it's actually very, very rare. I don't have an example of it, but what happens is if you imagine a cube, and I'll go to the slide here. Actually, I'm going to go to this slide. If you imagine the cube here, you know those 2 atoms that are here are actually pretty close to each other. So if you simply twist that top by a bit, which is what this is, we get a square antiprism. So just twisting this increases the distance between this. I mean, everything gets a little crowded here, right? So we have 8 atoms that are closely together. So this is actually the preferred geometry, is the square antiprism here, right? That's the same idea. This is the square antiprism, and the trigonal dodecahedron, which is what this is here. So did I have an example for that? Yes. Trigonal dodecahedron, this cyano compound here with molybdenum is what that is. Anyway, this is, oh gosh, we have AB9 here, the tri-capped trigonal prism. All right, so if we have a prism, I think I have a really good representation on this next one here, but if you draw, oh, it's really tough to see, but if you look at these 3 here, those are going to be the prism, and then it's capped on each side. Let me go to the next slide. This is actually really, you can really look down the prism here, and then it has 3 sides, of course, or 3 faces, and then each face has one as well. So that's 9. That's AB9. So just some examples of how crazy it can get. All right, that's it for VSEPR theory. The good news is I'm done with all of the basic background, and this time I promise you we're going to do point group theory, chapter 4. All right, see you soon.